Let's start our lecture. First of all, attention, next week we will have a theoretical test at the beginning of the lecture. We have only 2 lectures. We have 2 last lectures, and first of this lecture, now I'm going to consider the following topic, so-called bilinear forms. What does mean bilinear form? First of all, I recall what does mean linear map, and we define bilinear map. If we have 2 vector space, for example, first of them V and second W, let VW be a vector spaces. The maps F from V onto W is called linear map. If the 2 following conditions are fulfilled. First of them, if we apply our map F to the sum of any vectors U and V, we must obtain the sum of its images for any U and V from V. And second condition, if we apply our linear map to the products of scalar lambda and arbitrary vector U, we obtain the scalar product, this scalar. We obtain the product of the scalar lambda and image of vector U under this map F. Other words, if we apply our map to the vectors of initial vector space V, this maps acts with respect to the algebraic operations which defined on the initial vector space, and transforms these algebraic operations on the initial vector space V to the same algebraic operations which defined on the images, on the vector space W. The same way we can obtain the definition of the bilinear maps. Let, as before, we have 3 vector space V, U, and W. Vector spaces. And maps from the Cartesian product of vector space V and W to the vector space W is called bilinear. If we have the following condition: this map must be linear with respect to any elements. What does mean product of 2 sets? Product is a set of ordering pairs. The element of direct product is a set of ordered pairs. And if we fixed one of the element of this ordering pairs, we obtain the maps from one of these linear spaces to the linear space W. And the term bilinear means that this linear map, when we fixed one of the vectors of this product, must be linear map. Other words, we have the following condition. If we have three vectors v1 plus v2 and w, if we apply our map to such pair, the first element of this pair is a sum of two vectors v1 and v2, we must obtain the sum of the images f we apply to the pair v1 and u, and the second element of the sum, the image of the pair v2 and u. Other words, we have linearity condition with respect to first factors. And the same way, we have the linearity condition with respect to second factor. If a second element of our initial ordering pair is the sum of the some vectors u1 and u2, and if we apply our map to such ordering pair, we must obtain the sum of the images f v u1 plus f v u2, and we have the following two conditions, which the sum analogs of the first condition of the linear map. In the same way, we have three conditions of homogeneity, analog of the item 2 from the definition of the linear map. Namely, if we apply our bilinear map to the following pair lambda v u, where the first element of this ordering pair is a product of the scalar lambda and some vectors v, we must apply the product of this scalar on the image of the ordering pair v u for any lambda from the initial from the basic field k, this vector space over field k, and any v from v, any u from u. And the third condition, the same condition with respect to other factors of the ordering, to the other element of this initial ordering pair. If we apply our bilinear map to the ordering pair v lambda u, we must obtain the product of the scalar lambda and f u f v u for any lambda k and v which belongs to the capital V, u belongs to the capital U. And we obtain the definition of the bilinear map. What does mean bilinear form? Bilinear map. What does mean bilinear form? Bilinear form is a bilinear map when the vector space W is coincide with basic field. We will consider a case when our vector space is defined our real numbers vector field. Let V U be a vector space our real number field R. And in this case, form bilinear form F is a bilinear map from V times W onto real vector field R. We can consider some example of such bilinear map example. For example, let V be vector space Rm and U the vector space Rn. Let's consider some matrix AA. This matrix is a matrix which have the following size. This matrix has m rows and n columns. The size of this matrix m times n. Our basic field R. The entire of this matrix belongs R, or the entires are real numbers. And let X X1 Xm be the element of Rm, and Y Y1 Yn is the element of Rm. I will present these vectors, the element of these vector spaces, as vector columns. It's a general, as a rule, used such presentation. As a rule, the element of the vector space presents as a vector columns, but we can present this element also as vector rows. But this presentation used as a rule in many books, and we will follow such presentation. And let's consider the following form F x and y. We consider the product of the transpose vector x matrix A and y. And we obtain the following presentation: x1, xm, y1, yn. And we obtain the matrix product of the vector column and the matrix. As a result, such multiplication, we obtain the vector row. This product has one row and n columns. And we obtain following row: A11 x1 plus am1 xm. The sum A E one x E. E goes from 1 to m. Sum A E2 x A E n x I y1 yn. And after this multiplication, we obtain the following double sum: E goes from 1 to m, and J goes from 1 to n. And we obtain A I J x y y j. We obtain the following presentation to this bilinear form. Easy to see that this formula defined the bilinear form. How to check this assertion? How to prove that this formula defines the bilinear form? To prove this fact, we must to check this for condition. First of this condition, if we present the first vector x as the sum x plus z, and second vector y, we must do the proof that this value, the value of our bilinear form on such pairs of the vectors. The first element of this pairs is the sum of two vectors, is equal to the sum of images how to check this condition. We have the following formula for our map. Easy to see if we apply this formula to the ordering pair of the vectors x and y, we obtain, using this presentation, we obtain the sum real numbers, which is the result of such product. And by definition, if you substitute in this formula instead vector x, the sum x plus z, we obtain the following expression: x plus z transpose a y. If we apply transposition operation to the sum of the vector, we obtain the sum of transpose elements. And we have x transpose y plus z transpose times a times y. The operation of matrix multiplication is associative, and we can apply matrix multiplication to the first vectors. This one, which is sum of x transpose and z transpose and a. And matrix multiplication has the distributivity properties. And we obtain the following expression: x transpose a plus z transpose a times y. And on the next step, we can use distributivity property of the matrix multiplication, and we obtain x transpose a y plus z transpose a y. And as a result, we obtain that this expression is equal f x y plus f z y. And we prove the first property which define the bilinear form. The same way, we can check the item 2 of our definition. And the last step, we can easy to check the homogeneity property. For example, if you apply our maps to the ordering pair lambda x and y, by definition, lambda x transpose a y. Easy to see. If we apply operation of transposition to the product of the some scalar lambda and vector x, we obtain the product of the scalar lambda onto x transpose. And ay. And using the property of matrix multiplication, we obtain that this expression is equal product of the scalar lambda xt ay, and it means this product lambda f xy. And we check. We have checked. We have checked the third property of the matrix of the definition of the bilinear form. In the same way, we can check the same properties which are related to the second factors of our bilinear form. And this may be a most important example of the bilinear form. Most important example of the bilinear form. Easy to see that in the general case, we can obtain the same presentation to the arbitrary bilinear form. Maybe a question about this fact. Do you understand what does mean bilinear form? Not clear. This calculation, okay. Maybe some partial example. Okay. I repeat this. A is the arbitrary matrix. We fixed the arbitrary matrix. Okay. I suggest consider the partial case. For example, let A be 2 times 2 matrix. The partial case, maybe more simple case. A11, A12, A21, A22. We fix some matrix. The integers of this matrix are real numbers. Some real numbers. And let X X1, X2 be the vectors of the vector space R2. Y with the other vector, which has the coordinates Y1, Y2. We have the following formula. What does mean this formula? If we apply our maps to the such pair of the vectors, we obtain the result which defined by the following formula. The multiplication of the transpose vector X, matrix A, and vectors Y. I must multiply these three matrices. This vector column is some example of the matrix, and this vector columns is also example of the matrix row. And we obtain the following product: X1, X2, our matrix A1, 1, A12, A21, A22, and other vectors Y1, Y2. Okay, we have associativity properties. What does mean associativity? We can multiply this element on this, and this product multiply on this element. And we also can multiply this matrix on this element, and this product multiply from the left side on these vectors. And the result will be same. For example, we can multiply this vector on this. What we obtain? Easy to see. A11 x1 plus A21 x2. The second element, A12 x1 plus A22 x2. Do you understand it? Yes or no? Yes. And we multiply this row on this column. And what we obtain? A11 x1 y1 plus a21 x2 y1 plus a12 x1 y2 plus a22 x2 y2. And as a result, we obtain the following product. And we can rewrite this product using the notation for the sum. And I must, this product, easy to see, 1, 1, 1, 1, 2, 2, 1, 2, 1, 1, 2, 2, 2, 2, 2, 2. What does it mean? I must rewrite this formula as a product aij x I yj. And the second index I goes from 1 to 2, j goes from integer from 1 to 2. And we obtain the following formula. In the general case, we have the sum calculation, but we have arbitrary matrix from the arbitrary size m times n, and we have the vectors x which has m components, and the second vectors n has n components, and we have this product. Easy to see that this matrix has m rows and n columns, and such product is well defined. Because the size of these vectors coincides with size of the column of the matrix A, and the size of this vector coincides with size of the rows of this matrix. Each product is well defined. And if we multiply this row on this matrix, we obtain the matrix row which has the n elements, and any element is product of this this row on this column, this row, second column, and so on. And we obtain the same such formulas for the first element and for the n element. And we multiply this vector row on this column, we obtain this formula. I repeat this calculation. Do you understand this? Okay. Let's move. And we have some partial example, and we can write some formula if this matrix has for example, this matrix A has a following form 1, 0, 3. From this matrix, we obtain, using this formula, that our bilinear form has a following form: 2x1 square plus 3x2 square. Oh, I'm sorry. X1 y1 plus 3x2 y2. The following form. If you consider the two vectors x, if vector y coincide with vector x, we apply our bilinear form to the pair of the equal vectors x, we obtain the following expression: 2x1 square plus 3x2 square. Some example. such expression from the bilinear form is called canonical form. And the sum of the squares of coordinates is called canonical form. Now we consider the general case when we have some arbitrary bilinear form. Item 2. Matrix of bilinear form. The idea of our reasoning. If we have some vectors in the arbitrary, in the general vector space, if we choose the basis in the vector space, we can correspond or arrange to the correspond to this vector the coordinates of this vector, this ordering and tuple, order and tuple of the numbers. The same way, now we will see that if we choose the basis in the vector space V, we can correspond to the bilinear form, the sum matrix, the matrix of bilinear form, and we can present our arbitrary bilinear form in the same form as a product of the arithmetical vector, sum matrix, and other arithmetical vector. And this matrix is called the matrix of bilinear form. And let's suppose we have some arbitrary bilinear form. Let's V be some be an vector space our real numbers are, and let F be some bilinear form from V to the V times V onto R. Let's choose basis U, U1, Un of V. Choose some basis. And let X be the decomposition of the vector X in terms of the basic vectors UI. Xi are coordinates of the vector X in the basis U. In the same way, let Y is presentation the vector Y as a linear combination of the basic vectors Y, J. And let's consider our bilinear form. And we substitute this expression for the vector X and Y into formula of bilinear form. And we obtain this following expression. the sum E xi ui and yj uj. And we can use the second property of linearity, with respect to first argument. We obtain that this expression is equal the sum our indices I, xi, f ui, and second factor yj uj. J goes from 1 to n. And on other step, we can apply the linearity condition with respect to second factors, second element of the ordering pair. And we obtain we can use homogeneity condition, and yj we can rewrite as the factors in the expression of values of our initial of our bilinear form. And we obtain the following expression. Now we denote by aij the value of our bilinear form, which value we calculate if on the pair of the vectors u I and uj. If we apply our bilinear form to the ordering pair of the vectors from our basis, we obtain some numbers, and these numbers form the element of some matrix. If I denote this expression by aij, I obtain the following formula: the double sum j goes from 1 to n, I goes from 1 to n, aij x I yj, and aij is equal f ui uj. And I obtain the same formula as this example. But in this example, we have some fixed matrix A, which defines this bilinear form. But in this our reasoning, we start with arbitrary bilinear form. And from this bilinear form, we obtain the same presentation. But in this case, the matrix entire matrix element exactly is the value of our bilinear form on the ordering pair of the basic vectors. And this formula exactly is the definition of the element of this matrix. And such defined matrix is called matrix of bilinear form. Other words, the matrix, which matrix element are the values of our bilinear form on the ordering pairs of the vectors of the some fixed basis, is called the matrix of bilinear form A, and we will use the same definition as the matrix of the operator. We obtain the formula for the matrix of bilinear form. We have some analogy with the matrix of the operator. If you fix some basis, it can correspond to the bilinear form some matrix, which called as matrix of bilinear form. And this matrix is defined by the following formula. Matrix A, which defined the following formula is called matrix of bilinear form. Maybe any question? Do you understand? This is central notion of our reasoning. And the maybe important idea is following. We can present the bilinear form using the matrix, and any bilinear form can be written in the same form as a matrix product. But from such presentation, we need to choose some basis. But we have the following question. If we change the basis, how change the matrix of the bilinear form? The bilinear form, the matrix, we defined on the vectors, on the not on the coordinates, on the vectors. And if we change the basis, the formula for the matrix presentation also change. It's the same as in the case of the vectors. If we change the basis, we change the coordinates of the vectors. And we have the formula for changing coordinates if we change the basis. We can ask how to change the matrix of bilinear form if we change the basis. Do you understand what's the question? And now we answer on this question. We considered before the case, the operator, the case of the changing of the coordinates of the vectors. And in any cases, we start with two bases. Let E be one basis and U be other basis. And let E be the old basis and U be a new basis. Be a new basis. And let C be a transition matrix. transition matrix. The notion transition matrix means the following. We have the following relation. The new basis U can be obtained as a product of the vector row, which has as element of the vectors of the old basis E, and matrix transition as a result of such product is a new basis U. We also, using matrix notation, we can rewrite the vector X as the product of the basis E and coordinate vector XE. And let XE be the coordinates of the vector X in the old basis E. In the same way, let XU be the coordinate vector X in the basis U. And we have also U times XU. And let me have two expressions for our bilinear form. Now we can apply our bilinear form to the pair of the vector X and Y. And we rewrite the value of our bilinear form in the old basis. We can rewrite E XE is exactly equal XI EI, and U XU is exactly equal XI prime UI, XJ prime UJ. And the same way we obtain the same expression from the vector Y, from the vector Y. And let X is equal X I EI YJ EJ, and we obtain the double sum XI YJ F EI EJ. The same way, we can rewrite this expression in the new basis. xk prime uk y prime a ua, and we obtain double sum. Double sum. This expression we can rewrite using this matrix notation. In this expression, we obtain that the vector xe transpose this matrix Fe of our bilinear form and ye. Using matrix notation, the second formula can be rewritten in the same form: xu transpose fu yu transpose. So we obtain the two following formulas: fxy is equal from our hand this equal this formula, and the other hand this expression is equal this formula. Oh, I'm sorry. And these two expressions are coincide. And we have the following relation between x and xe. If we substitute this expression to this formula, we obtain that the vector x is equal exe and equal u and xu. But u is equal the products e and c. And from this formula we obtain the following expression, that the vector xe is equal product of the matrix C on to xu. This formula, the formula changing of coordinates of vectors when we change the basis. And if we substitute this formula into expression, we obtain that the last formula can be written in the following form. I can change xu on I'm sorry. I can substitute this formula can be I must substitute in this formula this expression. I'm sorry, in this formula, and I obtain. If I substitute this expression in this formula, I obtain C xu transpose and Fe C y transpose. And if you apply transposition operation to the product of the matrix, we obtain the product transpose matrix, but the products we must choose in the inverse order. And we obtain XU transpose T, C, T, F, E, C, Y, U. And we must compare this expression and this expression. Easy to see that these two expressions are equal. We have this equality, and this equality is fulfilled for the any vectors xu and x and y. And if we substitute on the place of these vectors basic vectors, we obtain that the matrix elements, this matrix and this are coincide. From this equality, it follows that the corresponding matrix Fu and this matrix T transpose FEC are coincide. And we obtain the formula for changing matrix of the bilinear form when we change the basis. The matrix of bilinear form in the new basis can be expressed as a product the transition matrix C and its transpose and the matrix bilinear form in initial basis. Easy to see that this formula is different. If we compare this formula with the formula to changing of the matrix of operators, we can see that these two formulas are different. In the formula for the changing of the matrix of the operator, C transpose of EC. If for the matrix of the operator, on the place of the C transpose, we have the inverse C. And in this formula, transpose the real different formulas. And it's important remark. And we prove the following proposition. If let V be a vector space, F is a bilinear form, U and E are bases of V. C is a transition. Then we have following equality. Then Fu matrix of bilinear form in the new basis is equal to product of the following three matrices: C transpose, where C is the transition matrix. Matrix of bilinear form in the old basis, E, transition matrix C. We have the following the following formula for the transition matrix. And this main result. And now we can prove the following theorem. If you have some bilinear form f, we will suggest that this bilinear form is symmetric. What does mean symmetric? If I change the order of the arguments, I obtain the same result if I apply this bilinear form. Such bilinear form is called symmetric. We also will use the following notion. We will say that vector x and y are orthogonal with respect f if the value of a linear form xy is equal 0 if I apply this bilinear form on two vectors. And we also suggest that the bilinear form fxx is not equal 0 if x is non-zero vector. Such bilinear form is called non-degenerate. And if fxx strictly greater than 0, if x is not 0, such bilinear form is called positive definite. And we also will set that the vectors E1, En are orthogonal vector F also form orthogonal basis. If these vectors are pairwise orthogonal with respect to this orthogonal with respect to this bilinear form. It means that the value of our bilinear form on the pair of distinct vectors is equal 0. The main result easy to see if E1, En is orthogonal basis, then matrix Fe is diagonal. Because Fe ij is equal 0 if I is not equal j. Do you understand that this fact? It's by definition. And the main theorem. For any bilinear symmetric form F exist orthogonal basis U with respect to this form. Matrix Fu of the form F in this basis is diagonal. Proof of this theorem. The idea is very simple. We repeat the orthogonalization process or algorithm by Gram-Schmidt to the case of symmetric bilinear form. The symmetric bilinear form is natural generalization of the scalar product. And we can apply this algorithm to this case. If we will prove by induction, and induction by dimension of the vector space V, let dimension V is equal n. If n is equal 1, easy to see that in this case, if any basis is orthogonal, and F can be as 0 form or non-zero. In any cases, any basis is orthogonal. And we will suggest that our hypothesis is true our hypothesis about existence of such orthogonal basis is true for n minus 1. And now we will prove this hypothesis for the case when dimension is equal n. Let's choose V1, some non-zero vectors, and consider the orthogonal completion with respect to our form. It is the same, this analog of the orthogonal completion in the case of the scalar product. Namely, we consider any vectors x of vector space V such that the value of our form, symmetric bilinear form, on the pair of such vectors x and v1 is equal 0. The main observation, easy to see that our vector space is a direct sum of this linear span of the vector v1 and this orthogonal completion. The main idea is the following. If we choose some basis in this vector space, and any vectors can be rewritten as a linear span of this vectors. And the vector v1 can be rewritten as a linear combination with these vectors vi, I. This expression we have that the vectors a1, an form the basis, and from this fact it follows that this decomposition is unique. And also, if we apply our form to this pair of the vectors, we obtain the following equations. Double sum vi xj f ij, and we obtain the non-degenerate non-zero linear equation, and the variables, the unknowns of this linear equation xj, and this homogeneous equation and the dimension of the space of solution such equation is exactly equal n minus 1. From this fact we obtain the dimension of orthogonal completion of the linear span of the vector v1 is equal n minus 1. It means the dimension of this vector space exactly is equal n minus 1. After them, we can use our hypothesis, and this vector space exists the same basis u2, un by induction. In orthogonal completion exist orthogonal basis. U2, UN. And we can put U1 is equal V1, and we obtain the vector U1, U2, UN form basis, from the basis of V, because orthogonal completion is a linear span of the vector U1, UN, and V is U1, and V is a direct sum of these vectors. It was proved above, and our theorem is proved. Any question? Do you understand? I repeat briefly the main idea. We prove this theorem by induction from a case when n is equal 1. We can check that this theorem is proved with a checking history well, and we suppose that our theorem is true for any space which has the dimensions, which has a dimension is equal n minus 1. After them, we consider the vector space V, which has a dimension n, and we choose the some arbitrary non-zero vector V1 and consider orthogonal completion of these vectors. And we prove that dimension of the orthogonal completion is exactly equal n minus 1, and we choose the basis in this orthogonal completion. After them, we consider union of this vector V1 and the basis of orthogonal completion, and this union is the basis of all vector space. That's all. But I have no time, but I announce there's some assertion on them which will be on the following lecture. We consider some example how to find the orthogonal basis with respect to the orthogonal form. And we consider other proof of this theorem, other two proofs. One of them used the so-called procedure Lagrange method to find the some orthogonal basis, and other some criterion by Sylvester, and this criterion contains the third method to find this orthogonal basis. This theorem proves the existence of such basis, and we also consider two algorithms how to find this basis, and this algorithm we will use on our seminars and control in the exam. And after last lecture, I sent the program and a preliminary version of the task on the final exam. Thank you for your attention.